So on to today, we are going to be looking at load testing. I'm going to be focusing on reinforced concrete floors, as I said, and we're just going to go through screw piles. I've got a little bonus feature of a timber floor research that we some research into loading of a timber floor that we've done as a company, which loosely fits in with today's theme. So let's get started. So before we discuss load testing, we need to take a step back. What's the purpose of load testing and why would we do it? So I'm going to talk about why we do it in the demolition industry, and that is essentially to prove that a piece of demo kit can track on a suspended slab. Typically, this is small excavators, brocks or skid steers, and we need to consider an allowance for debris loading as well in these assessments. So it's important to understand how these load the structure. Each applies loads in a different way. Excavators will typically apply loads over their toes in two small contact patches when they're operating in the worst case, or when their arm is perpendicular to the tracks. It will mostly load one track. A brock applies a series of point loads, which you can get off their data sheets from on the Brock website. And skid steers apply point loads from their wheels. We consider a couple of scenarios. So we consider when the skid steer is moving debris around the structure as well. So we also consider the weights of that. And if anyone's seen any skid steers moving around a structure, you'll see that it is realistic that they will get on two wheels. But this itself does not necessitate that we go into undertake actual load testing, because it depends entirely on the structure. It may not be necessary. So structures that we've come across over the years vary massively, and it's not necessarily appropriate for all structures to undertake load testing, and it depends on the type of structure. So we've got single span RC slabs, we've got single span continuous RC slabs, we've got two-way RC slabs, flat slab construction, rib slab, waffle slab, precast planks, and beam and pot floors. The structures that are being taken down vary massively in their condition and their age and their floor construction. So I say this is not a exhaustive list of the types of structures that you'll come across, but this is just a few that we've come across over the last few years. But the different floor construction and different span arrangement lend themselves to different approaches in analysis. And what's critical is that you consider the type of floor that you are analysing, because one size does not fit all. So to justify a slab is acceptable to load by the plant, there are several checks that we must undertake to verify this. First being to check the bending moment applied to the slab. When a simply supported slab is loaded, the top face will go into compression. If we look at this diagram, yes, it's up a beam, but it's the same principle for a concrete slab. You'll get a compression block at the top of the slab, and at the bottom of the slab, you will get a tension being taken by the reinforcement. And essentially what we are checking here is that compression and that tension, it doesn't exceed the capacity of the slab, or the capacity of the rebar, or the intention or the compression capacity of the concrete and compression. So if we see, and I've shown a very basic bending moment diagram, with a point load in the center, which would be the worst case for the machine operate. The machine would be worst case operating in the center of the slab. And one other thing that we need to consider is the load distribution across the slab. So again, this depends for a reinforced concrete basic slab. This is how the load transfer laterally would occur, but it depends entirely on the slab or the construction of the floor. For example, if you had a ribbed floor, how many ribs takes the load? It depends in each scenario. Secondly, we must check the shear in the slab. You can see from the comparison of moving the point load nearer to the support that we've now got a condition that loads the slab worse in shear but better in bending. So obviously we need to tailor what we do to ensure that we are checking the piece of the loading in the worst case that will be applied for both shear and bending. We also need to consider punching shear, and this can occur at the point of load application and at column heads if you have a flat slab. So we need to check that the shear stress at the punching perimeter, which is either around the load or around the column, is not exceeded. Where the load application is over a small area, for example, a Brock outrigger, the shear area will be lower, meaning the stresses within the slab are higher, and you'd be more likely to get this punching failure. As I mentioned earlier, certain types of floor construction can be more susceptible to this type of failure, for example, or to different types of failure. In this instance, a point load of a Brock outrigger may be considerably worse if it's applied in the center of between two ribs of a ribbed slab when compared to on a normal concrete slab, because you've got that thin section that may punch through. A punch and shear failure at a column is where the whole slab breaks through the column, so fails around the column and punches down, and the column would punch up. And there've been quite a lot of high-profile failures on car parks. This one here, I think it's Piper's car park, happened in the late 90s. Punch and shear is a critical check as it's a catastrophic failure condition, meaning that there's little warning before failure. So it's vital to ensure that that forms part of any check on the slab. So in order to verify these by calculation, there's two approaches. The first is a live load comparison. So based on the building's original use, we can look at the allowable loads that the slab would have been designed to resist. From this, we can work back to determine if we are loading the slab beyond the original design case. This can be used to check bending and basic shear in a slab. This check is simple when no load factors are applied, as we're working against known capacities. There are limitations to this. For example, if you've got smaller spans, you end up with a small capacity, which may not be representative of the actual capacity. Secondly, we've got full slab analysis. This requires full knowledge of the floor construction, and this includes an accurate cross-section through the floor, rebar size, the rebar spacing, the rebar depth. It may necessitate testing of the rebar to determine if it's high or mild steel. You can typically tell depending on whether the bars are ribbed or smooth, but we've come across some bars in the past that don't conform to these typical conventions. So this check requires a full analysis and is typically undertaken to the code of practice that the structure was originally built to. Depending on the type of structure and the extent of the works being completed on site, we may be in a position where the live load capacity of the slab does not provide sufficient capacity and the slab information cannot be verified. So, or perhaps you've got pre-stressed bars and we don't know what the pre-stress in the bars is. This is the case where load testing can provide a real benefit to the project. So we'd always recommend that load testing is completed following an initial assessment of the slab, and used to verify where a designer anticipates there may be more capacity than can be proven numerically. It's always best to get an expert opinion on whether we say on whether this is a reasonable approach, because backpropping is not certain that you will get additional capacity beyond an analysis, and backpropping is is commonplace in the demolition industry for justifying a load, an excavator on a slab in the temporary state. So the design of a load testing arrangement needs to consider the worst case loading scenario for the structure in both bending and shear. So as I say, you need the previous analysis to complete to understand that. It needs to apply this load to the structure in a representative manner to ensure that the loading aligns with what you are going to apply in the future. So in order to do this, we design a prop arrangement that pushes against the structure above when loaded by a hydraulic jack. We use a remote setup that allows the load to be applied from a position where you are not, or the engineer on site isn't sat on the same slab that's being loaded. And we don't recommend using a system where you use weights. The benefit of using a jacking arrangement is that if there is any movement within the slab below, the system unloads itself. Whereas if you had weights on a slab, then that's not the case. And it could lead to a runaway failure. We take readings of the deflections of the slab at the point directly beneath the load application, and this is done by a remote setup again from a point of safety. The load would be increased in regular increments with a dwell time between application of load. The load is the floor is inspected during the load application and through the load test by an engineer, and the load is increased up to 2 times the proposed applied loads, or up to a point where the engineer on site deems we should stop, because obviously they're going to be monitoring the structure. If there's any cracking, if the load versus deflection diagram that they are producing in real time with during the assessment isn't a linear line, there would be reason to stop the test, because we don't want to test to failure. So to run through this, I think it's best to run through a case study of how we've done this in the past. So this case study is the justification of plans track on Hartopp and Lannoy point towers. These structures are large panel system structures, meaning that they require particular attention. I'll refer you to our previous CPD seminar on LPS structures that I believe Josh previously gave, and you can find this on our YouTube channel. The floors of the structure were made of precast, pre-stressed concrete panels due to the floor small spans, the small floor spans, the uncertainty between the connection between the sides of the panels. We couldn't prove via calculation that the 3-ton excavator that our client wanted to use on the structure to demolish it could take the load. So we undertook load testing. Following the initial analysis, we found that the worst case bending moments were when the machine was operating on its toes in the orientation shown here, where this is the slab section. So we've placed that at the edge of the panel to test that interface and make sure that it is as we anticipate that the load either transfers or to test whether it does or doesn't. And similarly with the shear case, we've applied the load against the edge of the panel and towards the support of the panel. We obviously previously undertaken calculations to determine which was the critical check, and then implemented that on site. So in order to replicate the loading to the panel, we detailed a propping system that jacked off here. So if you can see my mouse, this is the point of load application. So if you see section C here, you would see this. So we've got two sections of SuperSlim here at the base, and they represent the two toes of the machine. And we've got, if you imagine, the load starts here and works its way up, because that's the point of application. So the point that's being loaded by this jack, and that's pushing up against these beams here, which are these beams here. That load is then transferred up and then transferred into the slab, and we've taken a portion of this slab's self-weight, and we are going up again, and we're taking a portion of this slab's self-weight to provide the load to push from onto the system, or onto this slab here. These sections here were just put in to aid buildability, but became loose when the load was applied. So that's how the moment was checked on the slab, and you can see here there's a photo of that, of the lower system during the testing or before the testing. Similarly, we've got the shear testing arrangement. Slightly different arrangement was used here due to the proximity to the edge of the slab. We found it best to put, so that you imagine the load's coming up here off the jack. We took the load and the vertical restrict, or the self-weight of the coming down the wall to resist against when we jacked from. We also included an additional prop to take out the horizontal force that we're applying to the wall. You can see here the jacking arrangement. A section through the test setup can be shown here. We detailed it so that the engineer can load the structure off to the side, as mentioned previously, from the adjacent bay. The load test is taken in increments, and yeah, essentially the engineer on site would monitor the slab as the load is applied very vigilantly, and that is how we undertook this load testing. I will now go to another example of a different load testing setup. So this project was completed, I want to say, about 5 years ago. It was quite a long while ago, this project, but it shows a similar approach, but to suit this structure and the structure that we are, the structure that we were going to load at the time. So we've put the force into the center of the slab here, and we've jacked off, and we've taken this point and this point to take the weight from what's coming down above here. And this test setup here is what that looks like at the bottom. To get the results, and you see we've got the lead, so this is again all done remotely. Here I've shown an indicative diagram of the applied load versus the deflection, just to show the type of deflection that we would be anticipating. And obviously the fact it's a linear line means that the slab is deflecting as anticipated, and there was no real cause for concern during testing. So this one is a bit of a bonus, and it's pulled off a research that we've done into loads being applied to timber floors. So if you imagine you've got a load coming down here onto your, these are, say, timber beams, large timber beams, and these are your timber joists. And we've got a load coming down centrally onto this point here, and we can't backprop this floor. So what we've done is we've placed a timber along the floor to distribute the load between several joists. That's the scenario, and here we've got a finite analysis model of that exact scenario, and we've also got on the right hand side a model test. So we ran these results to try and determine how essentially what the load in each joist was, and obviously that differs massively depending on the stiffness of the spreader beam, the stiffness of the joists, the span of the joists, several other factors. So in order to try and establish what was reasonable, how many joists you could reasonably transfer the load to, we have done a bit of testing, a bit of research. Because this graph at the top left here is one that shows testing of, I think it's a joist at 600 mils spacing, and I think there's lots and lots of different iterations of the spreader beams. I can't, doesn't tell you which joist that is, but essentially we've got many iterations of these tests that we undertook to try and come up with an easy rule for the future as to determine how to spread the load efficiently, and how big of a spreader beam we need and how many joists will get loaded. We did the in-situ testing on less different scenarios. So with the model testing, we did on, I think it was 3 or 4 different joist spacing types, and each different joist spacing there was different size of timbers used and different spreader beams used for each one. I think there was more than 30 different scenarios that we checked, and we also did the in-situ testing on a couple of them to verify the answers, which gave slightly different results, but the same principle. So the reason why these results were slightly greater is because I think of local crushing in the point of load application. So in summary from these timber floor tests, we found a general profile of, if you imagine you've got a joist here, you've got a joist here, got a joist here, a joist here. The joists are running into the page on this diagram. We found, roughly speaking, this distribution, where the central joist takes slightly more than the curve of the other joists. And we've calculated, based on this research, we've got quite a few equations out of it that give us a way to easily analyze this without having to go into a full analysis model each time. So it was an interesting little side project, as it were. Thanks for listening to my segment of this, and I'm going to pass you over to Richard to talk about load testing of screw piles.
Thanks, James. As he says, I'm Richard Boyle. I work in the West Midlands office with the always popular Josh. He's not here today, but he's joined the webinar to answer all the questions you might have later. I'm going to talk about.
I don't think I was going to say I'm going to answer all the questions.
You can answer all the questions you want, Josh. It'll be good. No, I'm going to talk about a slightly different scenario where we're load testing screw piles instead of testing the floors of the structure. And we've planned this very good, so I need James to do all my next sliding. So if you would be so kind. Before we get into the load testing, I thought we should probably talk about what screw piles actually are, because not everyone knows. Basically, they're a ground anchoring system for deep foundations. They work similar to traditional piles, but rather than using concrete piles, they're steel hollow sections with large screws. As you can see at the bottom there, they've got screws or helixes throughout them, and they have screws or a pile toe at the end. They go down quite far as well, down to the competent soil, further down than the shallow foundations can utilize. So if we can go to the next slide, James. Earlier on this year, we carried out a design for some screw piles and a grillage for a bridge abutment in the northwest of Birmingham. So the screw piles were to be placed in that arrangement you can see on the left there, and then we landed the grillage on top. But before we landed the grillage, we had to make sure that the screw piles would take the loads that we thought they would. The load testing carried out, if we can move on a bit, James. Yeah. So normally when you do load testing of screw piles, you take the capacity of the piles in their in situ condition. So this requires undrained conditions to be used to calculate the testing load that we take it to. In this case, we got that to come up to about 200 kilonewtons. And for the actual design of the screw piles, you need to take into account the undrained and drained conditions. So you have to take this into account when you're actually designing the screw piles and get the designer of the screw piles to give you the loads that are required to the testing. With some ground anchor systems, it is possible to test every anchor. In this case, with the higher capacities that we needed and the arrangement of the screw piles, it wasn't practical to test every pile. So we tested the key piles that would take the most loads in this situation, or the most critical piles. In this kind of testing, as you can see from the picture there, you rely on two or more of the adjacent piles to take a load and tension while you test the central pile. So on that middle pile, that's a slightly different color there, and you can see a jack was put at the top. The jack pushes up against the beam, and that pushes down on the central pile that you're testing. The adjacent two piles are they were welded to the beam in this case, and as you push up from that central pile, they take the tension load, and that allows you to carry out the testing. The deflection in the compression pile is recorded at different intervals with different hold or dwell times. We did the test normally about 2 tons at each hold interval, and then we left it there for a minute, and then we continued on till we get to the top load, and then we held it there for 10 minutes. I think we actually held it for 20 minutes in reality, but we had to have a minimum of 10 minutes. If you move on to the next slide, thank you. So in this case, we tested these 3 piles that are highlighted in red. The pile groups in the corners were the most highly utilized because that's where the bridge bearings came down. And so that pile in the middle of the group at the side is the ones that took the most load. If you want to click once, James, thank you. So that pile, you can see that you had adjacent piles that we can just take to use for testing. So it was the P9 pile was the one that we were testing, and the P6 and 12 were used as the tension piles. Because we already had them, we could just use these piles, and they didn't have to be sacrificial. They could be part of the design. However, with the top pile, and I think we need another click there, James. We needed some sacrificial piles to be added in at the top. I was on site and I foolishly didn't get a picture of these piles because all the testing went quite well at this stage. But if you move one more time, James, just to show where those piles went. Are you showing it? Yeah.
Yep.
And we can move on now. That was just showing where the sacrificial piles went. However, in this case, the arrangement for the corner piles didn't act as we wanted it to. Despite the size and the stiffness of that top beam that was there, it became clear that most of the deflection we were recording was from that beam deflecting and the piles next to it, the welds on it not being strong enough. So instead of going off, getting another welding arrangement and more connections, we decided to add more weight to the top of it. So as you can see, we did a quick rethink and we came up with this design to stop the beams from bending. We added all that weight. I think it was 4 concrete blocks that weighed 2 and a bit tons each. So altogether, that's 10 tons sitting on top of those beam arrangements that were sitting on top of all those piles. But this was only about half of the load we needed to get to anyway. So we still had to add a lot more with the jacks. And obviously this arrangement wasn't loading the pile we were testing directly. So when we went out on site and helpfully verified the record and read the deflection in the pile, it was more accurate to what we were expecting. We weren't getting interesting loads, interesting deflections even in that beam rather than in the piles that we were testing. We managed to get the loads straight up to what we needed, and we had very low deflection. It came around to about 3 or 4 mils. I think one of them got to 5 on the other side. And all that was well within the limitations of the testing. So the piles got up to their full capacity, if not more, in the ground conditions on site. It is important that when you're on site and you're testing piles, you can't be sure of the ground conditions unless you have a borehole or some kind of ground investigation at the very site that you're putting in the piles. Obviously, doing the borehole log disturbs the soil, which means you don't have accurate information for the long-term and drain conditions. So it's one of those things, if you look at it properly, it no longer represents what it actually is. So that's why you need to do the load testing. If we move on, I think that is the end of what I did on the load testing. So yes, that's just a happy man after the load testing, after all the rejigging that we had to do from the simple beam design to the more complicated cartilage design used as counterweight. And I think I'm passing back to James now, and he can go to the next bit.
Yes, essentially that is the end of our presentation. Today's topic was load testing.